VMware. We will have a discussion on the VMware next time. But the way the VMware workstation worked for the Type 2 hypervisor is that it acts as a normal operating system. So when we install when we have a newly installed computer, it expects to find either a CD or a DVD or a USB or some drive that contains the installation files for the operating system so we can install it. The VMware does the same thing, so it expects an actual drive with installation files. And so, of course, that's not an actual drive. We can have these installation files on some image on the hard drive, on the disk, and install it. And then when it's installed, it creates its own virtual drive, which also can be just a file on the hard disk. But let's look at this picture. What we have here is a Type 1 hypervisor which supports only one guest operating system. So just look on the picture. The guest operating system is sitting inside the process called virtual machine. So the hardware is here, the hypervisor is directly installed on the hardware, and then we have processes running on the top. The guest operating system is running in one of those processes. Now, it is an operating system, so it thinks that it's running in kernel mode. Look at the picture and see, is it really running in kernel mode? Is the guest operating system running in kernel mode?
No, unless you're not running.
It's not, right? Because what? Because the hypervisor is the only thing here that's running in kernel mode. Because the Type 1 hypervisor. We said the Type 1 hypervisor is the only program running in the kernel mode. Everything else runs on top of it in the user mode. So this guest operating system thinks it's running in kernel mode, but it's not. That's why we call it a virtual kernel mode. So what happens when the guest operating system tries to access the hardware? It needs to open a file, or it needs to print, or do something else. It has an I/O operation. What happens? It's not in kernel mode. So the CPU has a set of instructions which it can execute when it's in kernel mode. When it's in user mode, these instructions cannot be executed. Normally, if the CPU does not support this virtual technology, the instruction will fail and the operating system will crash. The guest operating system will crash. Because it's in user mode and trying to run a kernel instruction, the CPU does not support virtualization, it will crash. If the CPU supports virtualization technology, what this technology will do, it will allow the guest operating system to trap from user mode into kernel mode into its hypervisor, because it is running kernel mode. And then this hypervisor will access the hardware and return the results back to the guest operating system. So this is done in hardware by the CPU manufacturers. Now, before the CPU manufacturers created that, they were still virtual machines. There was the VMware Type 1 hypervisor that came out before Intel and AMD implemented this virtual technology on the CPU. So, how did they make that happen back then? Well, back at that time, they were the CPU supported several rings of privileges. So the operating system was always running in ring 0, which is the lowest number, that's the most privileged mode. And the user processes are running in the ring 3, the highest number, the least privileged mode. And then these two rings were available for virtual machines. So the VMware, the way they implemented it is they put the virtual machine into this ring 1, so it gave it some intermediate level of privileges. And this way it's also very close to the hypervisor, which is running in the most privileged ring. And what they did is they rewrote part of the operating system so that when it has a kernel mode instruction to execute, the binaries are cached inside the hypervisor, and it does it very quickly, because if it had to do it separately every time it traps into the kernel, it would be very slow. So whatever the guest operating system had to do, they did a binary translation and put that into a cache inside the hypervisor, so it was running much faster the next time. And eventually almost the whole system was cached and it ran pretty quickly. So they did So for this case, the kernel rewrites the code, or it does binary translation. One basic block at a time. And basic block does not contain any kernel instructions. So it takes whatever instructions were there and converts them into something that do not contain kernel instructions. And it puts it in the cache of the hypervisor. So there are no jump, call, trap, or other instructions like that. And it ends with branch. And this thing is cached and it can run pretty quickly. So in a sense, it tries to eliminate kernel instructions from the guest operating system by rewriting parts of the code of the operating system and caching it. So they did some careful programming back then, which was possible to do because we had these rings. So let's look at the two types we have discussed. We have two virtual machines here on the picture which support this virtualization technology. The first one, which is on the left side of this dashed line, is a Windows virtual machine, and it's an unmodified version of the Windows. So look here, we said parts of the operating system was modified or was rewritten. In this case, this version of Windows is unmodified, and unmodified versions existed like that because the source code for Windows was not available. So there was lack of availability of source code, and we could not modify the code. And if we cannot, then what happens? Then, when we have sensitive instruction that needs to access the kernel, we have to trap into the kernel, and these traps are very expensive and they slow down the performance of the system, so this virtual machine will be running very slow, but it's a true virtualization because this machine does not in any way realize that it's not in kernel mode, and it acts just like a normal operating system. On the other side, we have a modified version of Linux. That's why we have this power virtualization, which is what we explained earlier. It does not try to look like a true operating system that runs on the hardware, but instead it explicitly states that it's a virtual environment, and it's using an interface of hypercalls. So it's a modified version because the version no longer contains kernel instructions at all. So the operating system is rewritten or modified, so it does never call kernel instructions directly. Instead, when it needs the kernel instructions, it has an interface that it accesses, and this interface is called hypercalls. So pretty much acts as a user process that when it needs to do an I/O operation or modify critical registers or do something else, then it makes a system call to the operating system. So there's an interface of system calls that it can make to perform these functions. In this case, we have an interface of hypercalls that it can call that are served by this microkernel. So that's why we call it a microkernel, because it's similar to a kernel. So when the normal process needs to make a kernel call, it makes a system call and calls the interface. When the virtual machine modified Linux, in this case, hard virtualized, wants to make a system call, it calls these hypercalls, and that's why this is a microkernel. It's not a full kernel, it's a microkernel because it's much smaller than a normal kernel, so its functionality is limited. In particular, provides just basic services, such as process dispatching, managing the memory management unit, it does not do message passing. Or sharing of memory and things like that the normal kernel will do. And also, it's smaller in terms of the size, in terms of lines of code that it contains. It's much smaller than a normal kernel.